Hello everyone, and let's start with this presentation. Welcome everybody to RS3 webinar series part 3, and welcome to those of you who joined us for the first time and the rest of you who have been with us for the first two parts. Today we will be talking 3D slope stability analysis, and we will be using a couple of tools, and the emphasis would be on RS3. I'm Ali Reza, one of the geomechanics specialists at Rocscience, and I have with me Sina, another geomechanics specialist. The two of us together will be conducting this presentation. When it comes to slope stability, Rocscience has a versatile arsenal of tools that, depending on the problem that you're dealing with, we can apply the appropriate tool to that slope stability problem. The list can be categorized into two sets of algorithm that we are using here, except for rockfall here, that is a statistical analysis of pieces of rock falling from a slope. The rest of them, rock topple, rock plane, S-wedge, slide 2, slide 3, these are mainly basically using the limit equilibrium analysis. Just double checking the voice. Could you please, guys, confirm that you can hear us? We have a couple of, okay. Okay, thank you very much. Apparently, most people can hear us. Thank you very much. So the limit equilibrium approach that we are using in this bunch of softwares, it has some pros and cons. The pros would be that the limit equilibrium analysis approach is the most common slope stability analysis method that is practiced in the engineering. And geotechnical and mining engineers, they have extensive experience using this method. The formulation behind the method is relatively simple to understand and formulate and program. And the whole analysis is very quick. And because it is quick analysis, it can be used for evaluating sensitivity of failure to input parameters and also doing probabilistic analysis. And to define your model and materials there, geomaterials, you need minimal material input parameters. So this could be pros in that sense that you don't need many parameters to define your model. And the setback from that, you will see it in cons here later, that since you are not providing the stiffness of the material or neglecting the stress strain of the material, limit equilibrium cannot provide you information on deformation. The main issue, the main setback that we have for limit equilibrium analysis is that the failure mechanism and the mode of failure is assumed before solving the problem. Meaning that, for example, if you are looking at rock plane, you are analyzing planar failure in rock. If you are looking at S-wedge, you are analyzing surface wedge analysis. So these failure mechanisms are actually, we have embedded them in the name of the software. Like again, rock topple, this is used for coupling analysis. The slide 2 and the slide 3, these two are the most advanced softwares that we have for limit equilibrium analysis. These are very robust, very complicated programs, but the main mode of failure that they can address is sliding. So this failure mechanism, before running the problem and solving it, you are assuming that the failure mechanism that I'm going to solve for is this mode. And another con is that we have arbitrary and simplifying assumptions so that we can solve the statistic equilibrium equations in these methods. The other method that we have to deal with the slope stability problem is finite element shear strength reduction method. We have this method embedded, implemented in our RS2 and RS3, the 2D and 3D finite element program that we have. Comparing finite element SSR with limit equilibrium, these are the cons, for example, that we have for this method. Because we are running finite element analysis, it's going to take more time computationally to solve the problem. And we require to define more material input parameters. comparing to limit equilibrium, at least we need the stiffness and Poisson's ratio to define the behavior of material. Again, because we are running finite element, it's a little bit more complex, so it requires more numerical modeling expertise that is commonly taught to geotechnical engineering, for example, in undergrad levels. And one of the things that is a subject of discussion is the definition of instability of solution. What we will be using here, then we are using it in RS1, RS3, we use the non-convergence as the definition of failure. But sometimes non-convergence can be the result of numerical instabilities rather than the physical instability of failure. And since the solution that we provide with finite element SSR is rather time-consuming compared to limit equilibrium, the sensitivity analysis and probabilistic analysis is rather difficult using this method. If you have any questions while we go through the presentation and demos, please type in the question section, and we will try to address as many as possible as we can at the end of the presentation. Now, the pros for finite element SSR, the main one, in my opinion, is that you do not assume any failure mechanism before solving the problem. So, for example, on the right side, you can see a retaining wall, a supported retaining wall, for example. There are different modes of failure for this structure. It could be settlement, it could be rotation, it could be failure along the supports, it could be failure that goes through the support layers. There are various different modes of failure for just this problem. Other problems, they might have other combined modes of failure. When you use finite element SSR, you're not actually assuming any of these failure modes. The results of the analysis that you will get at the end of calculation is going to be your factor of safety and also the failure mechanism. Another pros that we have here, these methods can account for various material stress strain behavior. Because of that, it can provide information on deformation at working stress level, and also it can reveal progress and development of failure mechanism. The method, we didn't actually develop it here at Rocscience. The method is well documented in literature. For example, here from Bishop article presented by Bishop, I'm just going to read this phrase here. The factor of safety is thus defined as the ratio of the available shear strength of the soil to that required to maintain equilibrium. The shear strength mobilized is therefore equal to S, where, and this shear strength is the original shear strength divided by a factor. So this is that strength reduction factor that we are talking about here. The way it is applied, as a simple example, let's look at a very common failure criteria that everybody knows here, Moore Coulomb. When your shear strength criteria is described by Moore Coulomb, you have your original Moore Coulomb equation. Shear strength is equal to cohesion, effective vertical stress, effective normal stress multiplied by tangential friction angle. All of them in terms of effective stresses and effective properties. So this blue line in this plane of shear stress, normal stress, is your original failure envelope. Now, when we are applying that reduction factor, F, we are actually factoring this line, this stress envelope, by that factor. And that factor is applied in this form. And if you are looking at the properties of the material that are being factored in this case, for example, it's simply that the factored cohesion is going to be original divided by factor of safety, and the tangent of the factored friction angle is going to be equal to tangent of the original friction angle divided by the factor. When we are looking at this equation, some people might actually refer to it as C-phi method, but this is not C-phi method. We are actually applying shear strength reduction. So this method can be applied to any kind of strength envelope that you have, as we have applied it in our finite element program. Linear Moore Coulomb was rather simple to understand what's happening there, but we have many nonlinear failure envelope to define our shear strength in our programs. For example, here you are looking at General's Hook-Brown. It is nonlinear in the shear normal plane. And in 3D space, you have the effect of intermediate principal stress. and in the pipeline you can actually see the effect of intermediate principal stress and also the effect of the properties of the material, if it is more frictional or not. So all the complexities that we have here, depending on the nonlinearity of the shear strength and depending on the components of being more frictional or not, these are going to contribute to the complexity of this method. But all of that, we have got it handled and we have them in our programs. Now, what we actually do for finite element SSR, we are running a series of simulations. So these are the steps that we actually take. So we reduce the strength of slope materials in our finite element model by a factor, which is the strength reduction factor. Then we compute the finite element model. If the analysis fails and does not converge to a solution, we reduce the SRF and recompute the model. If the analysis converges to a solution, we increase the SRF and recompute. We do series of these simulations with different values of shear strength reduction factor, and the factor of safety is going to be the SRF that initiates the failure. Now, one thing that is very important here is the definition of failure. What is failure? In the literature, we have a couple of definitions for that, but the one that we are using here in RS2 and RS3 is the non-convergence of solution. That means that, okay, since we are solving for a nonlinear system of equations, and we are solving it using an iterative algorithm within a certain number of iteration and certain tolerance. If this solution algorithm does not converge within that certain number of iteration, that is called failure. And when that happens, there is no stress distribution in the domain that can satisfy failure criteria in the domain and also hold the global equilibrium. And again, when that happens, you will have rapid increase in nodal displacement in the domain. So this is the definition that we are using for that criteria of failure and where we define that critical SRF. Now, talking about failure criteria, the failure criteria that I will introduce in the next couple of slides, we have them all in slide 2, slide 3, RS2, and RS3. The library that we have is rather extensive, and I would say that these failure criteria that we have, I don't think anybody else has it in the practice. And so looking at this failure criteria, we have a library for isotropic strength criteria. We can categorize them into elastoplastic. These are the classic elastoplastic models like Moore-Coulomb, Hook-Brown, Drucker-Prager, Jonas Hook-Brown. And we have developed all the slide stress criteria that we have in our limit equilibrium packages. Those include Barton-Bandes, hyperbolic, power curve, shear-normal, Shantzip, and vertical stress ratio. So except for that Moore-Coulomb, the rest of them are nonlinear, and all of them, we have them in all these 4 tools that we present here. For anisotropic cases, we have jointed Moore-Coulomb, jointed generalized Hook-Brown, we have anisotropic linear, Snowden modified anisotropic linear, and generalized anisotropic. Just to explain what are these, I'm gonna go over 2 of these. This is the shear normal function that we have as one of those isotropic cases. This strength criteria allows the user to define any arbitrary shear normal function to define as a nonlinear Moore-Coulomb strength criteria for the material. So the case that you see here, for example, you have a bilinear case at the top, and the case at the bottom, you have numerous entities here in the tabular format, and you can define a curve envelope as well. The tabular values that you are seeing here, they could be the direct results of direct shear tests in the lab that are conducted under different vertical normal stresses. So direct results from direct shear tests, you can populate this graph and use it as your strength criteria. As an example, the embankment that you are seeing here, we are using a shear normal function and a power curve to model the strength of the material in this dam. And because we have the same strength criteria in our limit equilibrium packages and finite element packages, you can have a one-to-one correlation and comparison between these 2 methods and softwares. So this case, the factor of safety that we are getting from RS2, finite element SSR, is 1.97. The factor of safety that we are getting from slide 2 using limit equilibrium is 2. And as you see here, the red line here is slip surface predicted by limit equilibrium. And the contours that we see, the concentration of contours that we are seeing here, these are contours of shear strain. So where that is maximum, we have with your shear band or failure zone or slip surface. So in this case, the factors of safeties are matching. The location of the slip surface and the failure mechanism is matching. You can have a direct and accurate comparison between these two methods, both of them giving you the same factor of safety, both of them giving you the same failure mechanism. You can be sure that you have done your slope stability problem correctly and you move on. For anisotropic models, I'm just referring to one of them, the generalized anisotropic stress criteria. In this one, we allow the user to create a composite strength model in which they can assign any strength model to any orientation in 2D and 3D. But you see on the right side is a 2D representation of a rock mass. The rock is defined here, the gray material is defined using a generalized Cook-Browne criteria. The bedding plane, the orange zone, these are defined as more Coulomb, and the joints, the network of joints, these are defined using a Barton-Bandes criteria. Now, when you're looking at 3D configuration, you can represent these orientations of the bedding planes, the joints, by stereo net graphs. You can analyze all that in our DIP program, for example, and bring them into RS3 and Slide 3. Now, when you are looking at the general case of open pit mine, for example, that is excavated in an area that you have this kind of rock, depending on the angle of the cut that you have with respect to the orientations of these bedding and joints, you might have different failure mechanisms. So in some cases, you might have a slip along one joint. In another configuration, another cut angle, you might have toppling. So all these configurations, they can be handled properly using RS3. We have done an extensive verification program on this, and we have compared so many simulations. This is another case that I'm presenting to you. This one is using the anisotropic linear function. And in the definition of anisotropy and definition of the orientation for the bedding planes, we are using anisotropic surface. As you see here, once again, we have comparison between limit equilibrium and also finite element SRF. They both predict same failure mechanism and very close in factor of safety. Once again, so in these cases, you can be sure that you have done your slope stability problem correctly, and you can take the results and move on. That was a simple case. We have more advanced cases, for example, here. Once again, you have it in limit equilibrium, you have it in SRF. This one is using multiple zones of material. Each one of them, they use their own local anisotropic surface for definition of anisotropic layers. And the beauty about these two packages is that, let me just come out of this presentation. I'm showing you the slide model for that. When you want to analyze the same problem in using limit equilibrium and finite element SRF, you can actually open a new RS2 file. And if you have your slide model, I have the slide model saved here. This is that same model. You can just drag and drop it in RS2. When you do that, you will have this window coming up. It is suggesting that, do you want to run a stress reduction analysis? Because we are looking for slope stability, I would say yes. Automatically generate the mesh, okay. So your finite element SRF model is ready to be run. Then you can just click on compute and you will get the direct comparison between limit equilibrium and finite element SRF. It's quite easy to go from one tool to the other one. You can import, you can drag and drop. It's quite very easy and convenient. Okay, let's go back to the presentation. And using this functionality, you can have very accurate comparison between limit equilibrium and finite element. If the results match in terms of factor of safety and also the failure mechanism, you can be sure that you have done your simulation properly. If the results do not match, that means that, okay, you have to investigate it further. Now, we have a couple of examples in 3D using RS3. We have a levee with relief well, a dam, and an open mine. The first two, I actually introduced them in the last presentation when we were talking about seepage analysis. Now, we are looking at slope stability and factor of safety for these structures. So this is the levee that we had relief wells in it. The story of this levee starts with these 2D sections. So we had a 12 feet high retaining wall. On the upstream, you have the total elevation head of 115 feet. So this is where the water stands. And you have the downstream, that the elevation in the downstream is 106.5. We are analyzing for cases that you don't have any relief wells, and in the cases that you are installing, you are applying relief wells. Looking at it in 2D, we are comparing. On the left side, you have the case that you don't have any relief wells. On the right side, you have the relief wells. The purple line here, the magenta line, indicates the location of the phreatic surface. Comparing the figure on the left with right, you can see that when you have the relief wells, the water surface is dropping down to lower elevation. And because of that, we have the, based on the concept of effective stress, the one that has the relief wells, the level of effective stresses are higher. When your effective stresses are higher, just for simplicity, look at Moore Coulomb criteria, for example. Moore Coulomb criteria had sigma prime n multiplied by tangential friction angle. That was one of the terms in calculation of shear stress. So when your effective stress is higher, you will get higher strength. In this case, when we didn't have those relief wells and we had too much pore water pressure in the domain, the factor of safety that we calculated was 1.19 using finite element SRF and 1.18 using the limit equilibrium. If you have the relief wells and you drain the water out, you drop down your water table, your pore water pressure is lower in the domain, your effective stress is higher, consequently your shear strength is higher, your factor of safety is 1.65. So using that relief well, you have increased your factor of safety. But what we are looking at here again, we are looking at 2D sections. The assumption is that these are extruded. These relief wells are present in all locations. We're looking at the length of the levee normal to the plane that you are looking at here. Now, if in reality, the relief wells are installed at a certain distance from each other, for example, what I'm going to investigate now is the effect of the distance between these relief wells on the factor of safety. These are the steps that I actually took to generate that model before, to create that, to analyze for seepage analysis. We will look at project setting, create the geometry, use segmenter to generate those relief wells, or alternatively, I introduced the relief well entities that we recently developed in RS3. You assign your groundwater boundary condition, solid boundary condition, that includes the ponded water load. We mesh, refine the mesh if needs be. We compute, then we can take a look at the results. Now, just let me show you the model that we created. So this was the geometry of the model. Going to the project setting, these are the units. In the stress analysis, the convergence stuff is important. So we are using absolute force and energy. That's the one that we recommend. This is the one that triggers the failure or non-failure. In the groundwater tab, we are running a steady state analysis, and we are cutting the suctions with negative pore pressure cutoff. This means that above the phreatic surface, we will eliminate the suction in the calculation of effective stress so that we don't overestimate that. Based on that, we don't overestimate the shear strength. Then we go to shear strength reduction tab, select this one, then it's going to calculate the factor of safety, SRF, for you. In the groundwater tab, we have the total head upstream, we have the seepage face downstream, and we have these edges that I selected, and I assigned those relief wells there. Now, since we are running both solid and fluid analysis, in the loading tab, we have to assign those loads that are applied to the solid. The loads that we have here is the ponded water load in upstream. I am assigning that. If you look at it, the type of load that we have, it's a ponded water load, and it is coming from a constant head of 115 that we had in upstream. Now, we assign the restraint, we mesh it, then we can take a look at the results. The case that we are looking at here is the one that we have the relief valves installed at 50 feet apart from each other. Here you are looking at the total head distribution. Let me just show you the sections of this. 3D section. This is what we were actually looking at. These are the contours of total head in the domain. Now, this will be the water surface. If I go back to the all we used, we have 4 of them. The red one here, as you see it, this is the position that we have the water table. Now, let's go back to the 3D. Now, let's take a look at the result that we got for slope stability. If I switch to strain, maximum shear strain, this will show you where you have your maximum shear strain, which is the concentration of shear strain is going to indicate the slip surface. Okay, while this is loading, you can see that, okay, this is the failure surface that we have in the middle of the domain. And the other tool that we have here is the ISO surfaces. Sina will explain them later. In his example, I'm just going to activate them and show them to you. If you have them, you can see where you have the maximum values for it. Let me turn off the ISO surface as well. This is the location that you have all the concentration of shear strain and your slip surface. So the case that we solve here, the factor of safety is 1.54. If you look at all the factors of safety, the shear strength reduction factor that are applied, as I mentioned, we are running series of these simulation with different shear strength reduction factors, and we are looking at the one that are converged to solution and the one that don't converge. And as you see here, the green one are the ones that are converged. The red one, these are the ones that are not converged. And the one that is initiating the failure is going to be our critical SRF. So 1.54, here is the case that we are looking for. Going back to the presentation. So these are the results that we got for SSR-FEM. For the case that we had the relief valves 50 feet apart from each other. We are looking at total displacement on the left and total head distribution at the right. These are the shear strain distribution and shear strain isosurfaces. And we were looking at the effect of the distance between these relief valves. In the case that we didn't have any relief valves, the factor of safety was 1.19. We verified that with Levee is 1.18. The case that we had it extruded, and the assumption was that the wells are all over the place along the length of the domain, Levee, the factor of safety is 1.65. It is verified with the Levee as well, 1.63. And if you have them at a certain distance from each other, 200 feet, 100 feet, and 50 feet, you can see the effect of the distance of relief valves from each other as 1.37, 1.47, and 1.57. The model, in terms of geometry, looks like extruded, but this is not extruded model. This is, we are actually solving a 3D model because the boundary conditions that we have in this model is completely 3D. Thank you very much, Sina.
Hi everyone, thanks Ali Reza for the presentation. I'm going to continue the presentation with 2 other examples. Before I start, again, if you have any question, please write down in the question section. And for the ones that who asked the question, they notice that we have already answered the question, the written format in the same section. So if you ask the question, we're going to answer right away. Okay, this is the second example. This is the example that Ali Reza did in the previous groundwater webinar. What I'm gonna do, I'm gonna create the model again, but prepare it for the shear strain reduction method to do the SSR and calculate factor of safety. And at the end, we look at the results. Basically, for this model, we start with the project setting. We set up the project setting for this model. create the geometry. This is the actual 3D model. We import the DXF files to the model and create the volume. We have, as you can see here, we have a dam, we have the ground surface, and we have water table. We import the material from the models that we created before. We assign the boundary conditions, we mesh and compute, and then at the end we compare the results with the limit equilibrium method. Okay, let's start this example. I'm gonna open one RS3 software fresh. In the geometry section, you can import, export the DXF files, geometries that you have from other software packages. So I go to import, export, import geometries. I have a couple of entities here, two surfaces for the ground surface. As I explained the first webinar, we have a post-processing section. You can find and repair the defects of the surfaces that you import. So you can see that there are a couple of them. Near degenerated and near folding are not serious problems, but we can still repair the surfaces that we imported. And there is only one problem left, which is fine. We close it and we click on done, and the surfaces are imported. So we have surfaces. Now we need to create volumes. One of the methods to create a volume is going to geometry and create an external box around the surfaces that we imported. So let's modify this box a little bit. It has to be inside the surfaces, and for this example it has to be deep enough because we are doing seepage analysis. When I hit OK, you can see that the box is created and these two surfaces are cutting the box. To make different regions of material, we use a command called divide all geometry. Let's see what happens when I click on divide all. I use the default options. What's going to happen is these two surfaces are going to cut the external box into different pieces. So because we have two surfaces and one box, we expect to have three different materials. So the top one we are not interested, but we're going to keep it. I'm going to explain later why. And this is the topography volume that we have. Now we have to create a dam. As you can see in this view, we have two hills for this model, and we have to fill this gap with a dam. So what I'm going to do, I'm going to import a couple of polylines, which are the dam polylines, and you can see that this is here. By extruding these polylines, we are creating a volume to fill this gap between the hills. So we go to geometry, extrude. We have an offset option. This offset option, you can, for example, when I put -10, it's going to bring back the polylines 10 meters. The reason for that is I'm going to make sure that this dam is going through the topography and fill the whole place. And for the depths, I'm going to add 250. You can click on preview, and this is our dam. When I click OK, the dam is created. The ones that they have trash bins in front of them, they are not part of our external geometry to do the slope stability analysis. To make them part of the geometry, we have to do the divide all action again. But we don't need to intersect these pieces of geometry with the ground surface. So we change the role of the ground surface to construction, which means that the software is going to ignore it for now, and the software is going to intersect the top volume and these pieces of dam to make sure that we are creating different regions of material. So I click on divide all again. and let's see what's gonna happen. This divide all action is quite fast for most of the cases, and you can see that it's done. Not all of them are, they have a lock in front of them. The top one, again, we're gonna hide it, and these two volumes, we're gonna change the role to geology. So our model is ready now. If you want to look at the 2D cut, you can see that this is the model and this is the dam. There is no material assigned to different pieces of geometries. You can define the material, or you can import the material properties from the files that you prepared before. For example, we have an RS3 file, so I'm gonna use one of the files that I prepared, and I'm gonna import the properties from that file. So if you look at the material, you can see that these are the materials that we defined in the other file, and they are all imported. If we go to define material, they are all here. Again, we use the best way of assigning material properties when you have different pieces is to use the 2D cut. So I'm gonna assign different material properties to different sections. I start with the waste on the left, US field. You just click on the one on the left and then go to the right and click on the material. It's very easy and simple. It's done. I assign all the material properties. If we increase the transparency, you can see that this is the dam that I created. Okay. To go to the next step, first of all, it's always a good idea to follow these flow tabs. The next tab is groundwater analysis, but before that, we have to change the project setting. We have groundwater steady state and negative for water pressure cutoff to prevent suction. And also we are going to do a slope stability analysis. I'm going to turn on the determine strength reduction factor. Is okay. Now when we go to the groundwater tab, we can define the boundary conditions, groundwater boundary conditions. We have a total head of 240 on the upstream of the dam. And we have a seepage phase on the downstream. Since we have this groundwater condition, we have to add another piece of geometry, which is the plane, to consider this groundwater condition. We know that our water table is at the elevation of 240, if you can see in these views. So we have to make sure that we assign these boundary conditions at this elevation. So when we bring this plane in, we have to do the divide all geometry again to divide our dam at that elevation. So I click on divide all. So the surface is gonna cut my dam, and I'm gonna show you what's gonna happen. So let's look at the geometry again. So I use that surface to cut the dam. The reason for that is I'm gonna assign the boundary conditions to the upstream and downstream. When I click on upstream side of the dam, you can see that, sorry, this part is upstream. You can see that this region is selected. The reason that I was able to select this surface was because of that plane that I added to the geometry. So I'm gonna go to add groundwater boundary condition, and I'm gonna add a total head of 240 meters to this side. Also on the downstream of the dam, I'm gonna add I'm gonna select these surfaces and then go to the boundary condition, and this is the seepage face of the dam, like this. We also have ponded water for this example, so I'm gonna select the upstream of the dam again.
Just to address one of the questions that is asked up there, the way that we select these complex surfaces is that
yeah, I'll explain. This selection, phase selection, is to select the surfaces only. And if you keep the shift button and click anywhere on this surface, it's gonna select everything. So for example, let's say I want to select this again. I hold shift, click somewhere, and it's selected. Okay, to add ponded water, we go to the loading tab, add load to selected, change it to ponded water load, and as I said, we have the elevation of 240 meter, and you can see that this is added. We are doing a slope stability analysis, so we have to do restraints and we have to do surface restraints. We go to auto restraint surface, and you can see that we added the restraint to this model. The next step is mesh. In the mesh setting, the default is for the tetrahedra graded mesh. I use the default and I click on mesh. And the mesh for RS3 is a quite robust procedure, and it's very fast. So after the meshing is done, we can look at the number of elements that are created, and it's almost done. At the bottom here, you can see that the number of elements is 240,000 elements, which is a very good number to do a slope stability analysis. Below 1 million is always a good number. So the mesh is generated, everything is ready. If we go to the compute tab, we click on compute, it's gonna do the slope stability analysis. See, it's gonna take a while. I prepared this model before, and we are going to look at the results of the model. Okay, when we go to the results tab, before we look at the factor of safety results, let's look at the seepage analysis results. These are the results that Ali Reza showed in the previous webinar, but I wanted to make sure that everybody is looking at first. So we look at the total head for this model. As you saw, I defined the total head of 240 on the upstream of the dam, which is the red region. And you can see at the bottom that the maximum of the total head is 240. And as we go to the right side, this head of the water decreases. It's the same as the pore water pressure. Now let's look at the factor of safety results. First of all, the critical factor of safety is 1.37, which is the factor of safety calculated for this model. If you want to look at the location of the factor of safety, let me hide this first. When we look at the exterior contour, this is the location of the factor of safety. So the failure surface. The failure surface happened around the body of the dam. There are different ways of looking at it. One is like this exterior contour, or we can look at the section cut with contour plane, and you can see that this is the failure surface for this dam. Also, if you are interested in looking at maximum shear strain at different locations, especially the failure zone, you can define isosurfaces. Isosurfaces are 3D contours that you can set them in this option. For example, you can look at the contours with the maximum shear strain of 1. And since here our maximum shear strain changes from almost 0 to 1.5, so we define different values of maximum shear strain. So if I hit OK, it's going to create the isosurfaces for this model.
While this is being generated, I have a couple of questions I would like to answer here. This model, I ran it with using 10 noded tetrahedron elements, and it took like close to 2 hours to run. And yes, we are supposed to use 10-noded tetrahedron element for this. For the purpose of the demonstration here, we are using the 4-noded so that the meshing algorithm is going to be faster. Other than that, if you are solving for slope stability, you will have to use those higher order elements. Like in 2D, we are using the 6-noded triangle. In 3D, we are using the 10-noded tetrahedron.
Okay, let's keep going. So the region that is here, the blue region, is the region of the isosurfaces with maximum shear strain. And you can see that this is the failure zone for this model. You can also look at the total displacement to have a better idea of the failure surface for this model. So we go to solid displacement, total displacement. And we can look at the failure surface. This is the failure surface for this model for total displacement when we look at the total displacement. One of the features that the RS3 software has is to take a section, 2D section, and take it to the RS2 software to do 2D finite element analysis. To do so, there is an option here, RS2 section creator. If we click on this option, you can see that this is the section that we can create, section 1. You can look at the plan view. We created a section along the region that we had the failure zone. So if I click OK, you can see that this section is created. Let me turn on the material properties for this model. Turn this off. So this is the 2D section that we created for this model. And then if you click on open RS2 modeler, it's going to open the RS2 file, which I did here. This is the section that we created, and we took it to the RS2 model. You can see that this is the ponded water. We have boundary conditions. For the 2D model, we refined the mesh a little bit to make sure that the results at this region, they are accurate enough. So if we look at the results of this model, if you look at the maximum shear strain, you can see that this is the failure surface. Factor of safety is 1.3. You can also look at the total displacement. And this is the results for the total displacement. And you can see that this is the failure surface. So there is a belief that the results of 3D analysis is much larger than 2D. We have seen cases that they give a very similar result, or even 2D gives a little bit higher than 3D. Depends on the complexity of the model, and depends on the location of the 2D cut that you have from the 3D model. The results might change. For this model, the model is actually quite simple, and the location is right at the center of the failure of the 3D. So we expect that the results should be close in 2D and 3D, which we've seen in this model. We created the model in the Slide3 software, our 3D limit equilibrium software as well. The advantage of Slide3 software is that it has a very strong engine to calculate factor of safety and failure surface. We have cuckoo search and surface altering optimization technique. And you can see that the factor of safety is 1.35, very similar to the factor of safety that we have in the 3D RS3 software using finite element analysis. So when you set up the model correctly, these two software packages, they need to give exactly the same answer. Okay, let's continue. We have one more example. So we looked at the total head distribution for this model. We look at the total displacement, factor of safety of 1.37. We looked at the shear strain and also isosurfaces for maximum shear strain. And we compared the results of Slide3 and RS3, which gave the same answer. The next example is an open pit mine. This example, we created it in the Slide3 software. As I said in the, I think, first webinar, that geometry creation in the Slide3 and RS3 are exactly the same. So You can create a geometry in the RS3 software, or you can create it in a Slide3 software, export it, and import it into the other software. Or there is another option which we used here: create the model in the Slide3 software, do the limit equilibrium analysis, and import the whole thing as a project into the RS3 software. So this is what we did for this example. We had one anisotropic surface for this model, and I'm going to show you how we created it. And then we imported in RS3 mesh refinement if it's required, and compute and look at the results. Let's look at the model in the Slide3 software first. This is the Slide3 model. To create this model, we had several surfaces. You can also have, to assign the material, you can have boreholes to create the regions of material and assigning material. So we set up the model in advance. If you want to look at the 2D sections, you can see that we have different layers, we have different types of material. Looking at the material region, first of all, we had a surface that we needed to assign this surface as an anisotropic surface. To do so, we went to the define material first, and we defined two different materials as base material and bedding. Each of them, we defined them using the Shear-normal function, the nonlinear Mohr Coulomb that Alireza explained. So for bedding and rock mass, we have a Shear-normal function. Then we use the generalized anisotropic model, and we define the base material as the base that we had here. We define the bedding, and we use the surfaces that we define as our anisotropic surface. So this is the model setup. And then we did the computation, and this is the factor of safety and a slip surface. Factor of safety is 1.45, and the failure surface happened on the west side of the model. So what I'm gonna do, I'm gonna import this model into the RS3 software. So if we go to File, Import the Slide3 project, you can import any Slide3D model that you have. So for this model, we prepared one Slide3 that I showed you. So what's going to happen is the software is going to read the geometry. It's going to bring the geometry. It's going to bring the material setup, and it's going to bring any anisotropic surface or any material properties that are defined in Slide3. Because as Alireza said, all the libraries of material in Slide2 and Slide3 are available in RS2 and RS3 as well. So we don't have any problem importing one to the other. So this is the anisotropic surface that we had. These are the material that we define. And if we go to the material section, you can see that the bedding and base, they are defined with Shear-normal function. And if we go to material 3, it is defined in the same way that we define in Slide3. The next step is, the other thing is, if we go to a project setting in the shear strength reduction, because we imported from Slide, the SSR is automatically activated because Slide is a slow stability software. So what we do is to find factor of safety. For restraints, again, we add surface restraints, and next we have to add mesh. When you import a project from a Slide, the default mesh is uniform 10-noded tetrahedral. I'm going to change it to graded. For graded option, this is a new option in the RS3. You can define the minimum and maximum size of the elements that you want. For example, if I define 10 for minimum, 100 for maximum, it can be easily done. You can also define different levels of gradation. So after meshing, this model is done to compute. I prepared the mesh in another file because I did part of refinement as well. The reason that we did it we did the refinement was because we knew that the failure mechanism, the failure surface happened on the west side of the model. So I created a box on the west side of the model, and I used it to refine the mesh. So the actual mesh was 1000, and I used the box to refine the mesh to 5. So this is easily possible, and you can see that the mesh on the west side, as you can see in this picture, is finer than the other sides of the model. Also, another option that we have in the RS3 software, you can see that when we created the geometry, there are some sharp edges for the model. These edges might be problematic in the finite element analysis. You may have large displacement or large strains at these corners and these sharp edges. To prevent that, we have an option in the RS3 software which is called SSR exclude area. So I defined a small box at the top of the model to exclude that region from doing the shear strength reduction model. On the other hand, you can do something else. You can define this box that I defined for mesh refinement and set this section as the SSR search area. So set SSR area. It's gonna do the calculation of the shear strength reduction only for this region, because you already know that the failure is gonna happen on this region. Okay, let's look at the results. We don't have that much of time. So factor of safety is 1.45, similar to the Slide3 software. I also brought the Slide3 results. This is the black line is the Slide3 result. You can see that they match with the RS3 results. You can also look at, instead of exterior contour, you can look at the contour plane for this model. So if we look at the contour plane, you can see that this is the critical slip surface for the total displacement. You can also change it to the maximum shear strain and see the failure surface using the maximum shear strain, and you can see that this is the failure surface that we have with the maximum shear strain. Okay, let's go back to the presentation. So for this model, we have the results of the shear strength reduction method. Total displacement, maximum shear strain, we show them as a cut. We can also compare the results with the slide software. We got exactly the same answer, the same region, the same failure mechanism, and the same factor of safety. Okay, I think we responded to all the questions, and if you want a trial version of RS3 software or any other software packages, please go to rocscience.com trials.
If you have any further question, please email us. We try to address them as adequately as possible. And thank you very much for joining us, and hope to see you in next webinars. Depending on your request, we will arrange them for you. So if you have any future requests to be described in, explained to you in a webinar, please let us know. We can arrange them for you and we will present them to you. Thank you very much.
Thank you.